Welcome back to Logic, Language and Information. In this lesson, we'll get down to business, doing propositional logic programming in PROLOG. At the end of last lesson, we reached a compromise point. In order to find decidable and practically computable classes of logical consequence problem to implement on a computer, we'll make some restrictions. We're going to restrict to a simple fragment of the language and use a system with only one proof rule. Logic programming is a direct, declarative style of computer programming, which involves writing what you want to compute, but not how. This is in contrast with procedural programming languages such as Java or C, where the program explicitly describes the steps of computation. Begin with a restricted class of formulas. A program clause, also called a definite clause, is either a fact, a single atomic proposition on its own, or else a simple conditional whose consequent is a single atomic proposition, with the antecedent a conjunction of atoms. If there are 0 atoms in the antecedent, then the conditional reduces to just a fact. A logic program is a list of program clauses, and we can treat the whole program as the conjunction of its clauses. Think of a logic program as a database of information in a domain of knowledge. A goal is simply a list of atoms, and the corresponding goal formula is the conjunction B of those atoms. With these restrictions, the automated reasoning task of interest to us is whether or not a given goal, G, is a logical consequence of a logic program P. Recall this requires a truth-transferring relationship. For every way of valuing the atoms, or for every row of the truth table, if evaluation makes all of the formulas A and P true, then it must also make the goal formula B true. Let the P's and Q's be all atomic formulas, and consider the 5 options shown. Which of these are logically equivalent to a logic program? That is, either a program clause or a conjunction of program clauses. Take a few minutes to work on this yourself. You'll need to remember various logical equivalences from the core propositional logic. So how did you go? For A, the answer is going to be no, because there is no way to rewrite the disjunction Q1 or Q2 as a conditional of positive atoms. It comes out equivalent to not Q1 implies Q2. For B, we used De Morgan's law and the material conditional equivalence to rewrite the formula shown as P1 and P2 and P3 implies Q, which is a program clause. For C, we can distribute AND over the conditional to get a conjunction of program clauses. For D, the answer will come out no, because there is no corresponding distribution of OR over the conditional. So the disjunction Q1 or Q2 and the consequent is stuck there. And finally, for E, a run-on conditional of this form can be equivalently rewritten as a standard program clause, as shown. If you have any more questions or comments, look first in the course notes and then go to the discussion board, and I'll check in with you there. The programming language PROLOG has a few quirks to it. The most immediate is that program clauses are written in reverse. The consequent or head atom is written first, and the symbol :dash is written for the reverse conditional, then followed by the list of antecedent atoms, if there are any, none in the case of a fact. The reverse order will make more sense when we see how PROLOG works in lesson 6.4. It is the head of a program clause that has to be consulted first in a PROLOG query. We read a conditional program clause as Q if P1 and P2 and so on up to PM. Clauses of this form are sometimes called conditional rules, with head Q and body made up of P1, P2, and so on up to PM. For a simple fact, Q, it is all head and no body. There are some syntax restrictions in PROLOG. Names for atomic formulas must start with a lowercase letter, but can then be followed by uppercase, lowercase, digits, or an underscore symbol, but no others. Every program clause must end with a period or full stop, and the order of atoms within a clause and the order of program clauses within a program will turn out to really matter for how PROLOG executes, which will become clearer in Lesson 6.4. A PROLOG program P is written as a list of program clauses, each ending with a full stop, and saved in a plain text file with file type .pl. As before, we think of a logic program as a database of information about some subject domain. Again, as before, a goal G is just a list of atoms, which are entered after the PROLOG query prompt, $dash, and also end with a full stop. With these minor syntactic changes, we have the same automated reasoning task. Determine whether or not a given goal G is a logical consequence of a PROLOG program P. A point worth noting is that while the order of conjunctions does not make any difference for the meaning of logical consequence, the order of clauses written in a PROLOG program and the order of atoms within each clause will really matter in how PROLOG runs. Again, wait for Lesson 6.4. Time to get straight into an example. Consider the following bit of weather data expressed in a PROLOG program. It's rather salient to me as these lessons are being recorded in the middle of the Australian summer, with high temperatures and high fire danger becoming an increasing problem over the last few years with global warming. We are located in Melbourne, the capital of the state of Victoria, and in the central part of the state. There is a little town with the great name of Yackandandah in northern Victoria, which is usually hotter than Melbourne. Okay, with that preamble, the PROLOG program declares that it will be windy if you are in Melbourne and also windy if you are in Yackandandah, light rain if Melbourne, while dry if in Yackandandah. Continuing with broader level weather forecasts, it will be hot with temperatures of at least 35 degrees Celsius if you are in northern Victoria and mild with 25 Celsius if in central Victoria. And this is a wish for us at the moment. The next two clauses record that you are in central Victoria if you are in Melbourne and in northern Victoria if you are in Yackandandah. The last conditional says there is high fire danger if it is windy, dry and hot. The final fact expressed in the program is that you, the user, is in fact in Yackandandah. So, we load the program into PROLOG and at the query prompt put forth the goal, high fire danger, full stop. We press the return key and what happens? Oops, PROLOG complains. It cannot find any program clause with head Melbourne, so that atom is declared undefined. The way round this is to add an extra clause that is a tautology, is always true. Let the word false denote the constant proposition that is always valued false. Then for any atom P, P if false is always true because it is a conditional with a false antecedent. In particular, Melbourne if false is always true. So we can safely add it to the PROLOG program without changing the meaning of the program. So we load the revised program into PROLOG and at the query prompt put forth the goal, high fire danger. Press the return key and what happens? This time it comes back true, which is what should be expected. The program P says that high fire danger is true if it is windy, dry and hot 35. P also says that the user is in fact in Yackandandah, that it is windy and dry in Yackandandah, and that it is hot 35 in northern Victoria, which includes Yackandandah. In general, to get PROLOG to answer the question of whether or not G is a logical consequence of a logic program P, we load the program file containing P into PROLOG. We enter the goal atoms of G in a list after the query prompt and end the list with a full stop and press the return key. Then PROLOG will either answer true or false, meaning yes or no, to the logical consequence question, or, these are not the only options, PROLOG might get stuck in a loop and crash. Or another option, it reports some other error, like an atomic formula being considered undefined. As well advertised, it will be lesson 6.4 when we get to see how PROLOG actually produces its answers, or gets stuck in a loop. The short explanation is that, like the proof tree method we've seen in the core propositional logic, it is a refutation procedure. In effect, PROLOG supposes that all the clauses in P are true, but that the goal G is false, and then tries to derive a contradiction. Unlike the proof tree method, there will only be one inference rule, called resolution. Now, perhaps you are worried that program clauses and goals are rather too restrictive and too small a fragment of logic to be of much practical use. Well, think again. A recent use of PROLOG is in IBM's top-of-the-line artificial intelligence computer called Watson. Watson uses the predicate logic version of PROLOG rather than the propositional. If you stay around for LLI2, you'll see that. It was first developed to compete on the US TV game show Jeopardy! Armed with the entire contents of Wikipedia and a great deal else in its knowledge database, and equipped with PROLOG for computing logical consequence, Watson consistently outperformed the champion human competitors on the game show. Now, you're all encouraged to install a version of PROLOG on your local computer, if you can, and start exploring it yourself. We recommend the free open source implementation called SWI PROLOG, which has been developed at the University of Amsterdam. There are versions for Microsoft Windows, PCs, Macs, and for Linux and its variants. This brings us to the end of this lesson introducing PROLOG. At this stage, if you are eager, you can jump straight to lesson 6.4 and find out how PROLOG works. In lesson 6.3, we'll undertake a project in PROLOG, solving Sudoku puzzles, where you'll get some practical experience putting PROLOG to use. So see you then.